All right, here we are for another week of distance learning. Hope you guys had a good weekend. Let's get back to work. But before we do, I want to thank you for the mountain of jokes that I received last week. I think my favorite one so far was, what does the mathematician plow his field with? A protractor. Yeah, protractor, you measure angles, and tractor. You know it. All right. Okay, so I want to start with a little bit of review. I noticed in the Socrative quiz there was a couple things that were continually missed that we need a little bit of help on. But first, we've got a quadratic equation. We know it's opening down, right? The vertex is here. We've got our x-intercepts, all that good stuff. But the domain, or just a reminder on domain and range. Domain is all of your x values, and range is all of your y values. So when we look at a graph, and even if we look at the function, is there any x value that we cannot plug into this equation? Like if I want, I can plug in any number I want for x. It doesn't matter. I can plug in 4 billion if I want to, and I can get a solution. So as far as the x's go, we can use any number. So we call that all real numbers. The way we can recognize it from the graph is because the function is going left and right, it's still going to the left, it's still going to the right, it'll eventually go to every x value in the negatives, it'll eventually get to every x value in the positives, so it reaches all of the real numbers. As far as the range is where we have to be more specific. The range is all of the possible y values, and we always go to the vertex. So if I go to this vertex, which is at the ordered pair 1, 2, I know that this vertex is also my maximum for the graph. It's my maximum height that I'm going to reach. So the maximum height that we reached is going to be our y value. And if we go over here, that's a y value of 2, right? Our y value of 2. So this graph will never go above a y value of 2. So every y value on this graph has to be less than or equal to 2. We're definitely below 2. Right here we're equal to 2, but we never go above 2. What that means up here is I can plug in any x value I want, but no matter what I plug in, I will never get an output, right? F of x is the same as y. I will never get an output that's bigger than 2. No matter what number I plug in, I will always get something that is 2 or smaller. Okay, the y-intercept, you guys have done solid with that, right? We just look on the graph, see where we're crossing the y-axis. The zeros are our x-intercepts, which is another thing we're doing well with. So our x-intercepts, I can look right here, which is that point, which is also one of our y-intercepts, or our y-intercept. But we have a second 0 or x-intercept, which is right there at 2, 0. Right? So those two things we're doing great with. The interval of increase and the interval of decrease, though, I would say this is probably the area that we struggled with the most. So I just wanted to review that one more time. When we're looking at the intervals, we are looking at our x values. We're not looking up and down at all. We're only looking side to side. So one way I like to think about it is draw my axis of symmetry, which goes through an x value of 1. I just covered it up, but I promise it says 1. So x equals 1. And then if I draw the left edge of the graph, which x value is furthest left on the graph? Well, the x value that's furthest left on the graph is negative infinity. Right? That's the furthest left we can go. And then if we look the furthest right we can go, the furthest right we can go is x equals positive infinity. So our graph all the way to the left goes to negative infinity, but all the way right, it goes to positive infinity. Our axis of symmetry is important because this is the place where my graph stops increasing and begins decreasing. Or in some graphs, it's flipped. So I know that this graph is increasing for this entire interval. No matter where I am between negative infinity and positive 1, anywhere in this section of the graph, my graph is increasing. So the interval of increase is from the x of negative infinity until we get to an x value of 1. So interval of increase from negative infinity to 1. Now in this section of the graph, so from my axis of symmetry over, right, until forever, in this section of the graph, which direction is the graph headed? Well, the parabola is going down. So in this section, from positive 1 to positive infinity, the graph is always decreasing. So from 1 to infinity, the graph was going down. So the interval of decrease is from positive 1 to positive infinity, because we're not looking at the fact that it's going down. For our interval, we're putting the x values. So my x value is infinity, and between 1 and infinity, that graph is decreasing. All right, on to the new stuff, which does have some review in here as well. So first off, I want to look at factored form again. We talked about factored form a lot last week. Here's a specific problem in factored form, and I went ahead and graphed that problem over here. What do we know from factored form? So from factored form, we know two main things. We know that because it's positive in the front, right, that's our a value, our a is 1, we know the graph opens up. Right? And if it opens up, like this one opens up, it means we have this point down here, which is called a minimum. So every function in factored form will tell me if it opens up or down. The second thing factored form tells me is the two roots. So I know that the roots are going to be the opposite of the number here and the opposite of the number there. So the opposite of negative 2 is positive 2, and the opposite of negative 4 is positive 4. So I know that my two roots, or x-intercepts, are positive 2 and positive 4, which if I look at the graph, this point right here is 2, 0, and this point right here is 4, 0. So just like we knew, because of this, we knew the roots were 2 and 4, and if we look at the graph, sure enough, they are 2 and 4. So that's factored form. If we move to standard form, it gives us some of the same information, but also some new information. So the first thing I want to show is, how does factored form connect to standard form? Well, if we take the problem we just did, right, same graph because it's the same problem, how can we turn this into standard form? Well, that's very simple. We can take our two factors, we can plug them in the box. So x minus 2 I'm going to put on top, x minus 4 goes on the outside, and then if I multiply those together, I get x squared minus 2x minus 4x and plus 8. So we end up, once we combine these like terms, with x squared minus 6x plus 8. And so if we're putting that in standard form, well, there it is. The only thing we really have to do for graphing is just put f of x in front, right? That's our actual function. So f of x equals x squared minus 6x plus 8. So that is our standard form. Once we put the equation in standard form, what two things do we know? Well, the first thing is our a is positive. So a is a positive 1, which, as we did on the last slide, we know that means it opens up. And because it opens up, it has a minimum. Does standard form give us the roots? No, it does not. We would have to factor the problem and get it back into factored form to find the roots. But what else does the standard form give us? Well, hopefully you remember, the c value is always our y-intercept. So since c equals 8, our y-intercept is 0, 8. And if we go look at the graph, sure enough, there's my y-intercept, which is at 0, 8. So each form gives us something different that helps us know some information about the graph. Well, today we're going to introduce a new form. It's called vertex form. The equation for vertex form, we still have a, right? All three forms have an a out front. And then we have x minus h squared plus k. So we'll talk later about what h and k mean. My first thing that I want to do is I want to show you how we connect from standard form to vertex form. So from factored form to standard form, we just multiplied. To go from standard form into vertex form, we're actually going to complete the square. So you might remember completing the square a couple weeks ago. Hopefully you do. So if I take this problem, I do x squared minus 6x plus 8. Sorry, there's not supposed to be an x there. My bad. Equals 0. When we completed the square, the first thing we did was we moved the c to the other side. So we have x squared minus 6x plus the new c value equals, if we move this over, we have to subtract 8, right? So that gives me negative 8 plus whatever new c value we find. And then we went to the box. We put our first term in our first box. And then we knew to get a perfect square, we had to cut the negative 6 in half. So negative 3x, which if we start to factor this box, we get x minus 3, and what new number has to go in here in order for us to complete the square? Well, to get this box, we have to do negative 3 times negative 3, which is a positive 9. So 9 is the new number that we added in to both sides. And then we could rewrite this as a perfect square. We get x minus 3 squared equals negative 8 plus 9, 1. Now here's where we stop completing the square for when we want to put something into vertex form. To put it into vertex form, the last thing that we need to do is actually move this value back over to the left side. So if I want to move the 1 back over here, I just have to subtract it from both sides, and I end up getting x minus 3 squared minus 1. And then to make it a function, instead of equal to 0, I can just write f of x. And so we have now taken that same graph that we've done on 3 slides now, and we've put it into vertex form. So x minus 3 squared minus 1. Now what do we know? I don't expect you to know right now what we know about this graph, other than if a value is in the front, what's our a value? Well, our a value is still 1, right? It was 1 for the other 2 graphs. It's the same graph, which means our graph will open up. And because it opens up, it has a minimum. Now, what else do you think vertex form is going to tell us? Yes, the vertex. All right, so we're gonna start exploring, and then we'll come back and see how we can use this to identify the vertex. All right, so that was a little introduction, tie all of it together, and start to introduce vertex form. So, vertex form will give us, yes, we talked about it, the vertex. The A still tells us up or down, and then the vertex will be located at HK. Now what I want you to notice is H is inside the parentheses, and it has minus, a lot like factored form, where it had the minus. So whatever number is here, let's say it's minus 2, we know that because it has the negative in here, what we put here will actually be the opposite, just like when we did factored form. But the K has a plus. So when we know this number here, we're just going to put it there. We don't have to change the signs. It's not like factored form. So, some examples. This is in vertex form. We know that the vertex is at HK. And we know that in the equation, the H was negative. So we're going to do the opposite of negative 5. So the x-coordinate of our vertex is the opposite of this, so positive 5. But the K is just whatever is here, which is a positive 7. So our vertex has a y-coordinate of 7. So our vertex is 5, 7. The other thing I wanted to look at is whether or not the vertex is a maximum or a minimum, because we know the vertex will always be where our parabola changes direction. Well, how would I know if it's a max or a min? Well, what does the A value tell us? Because the A is positive, we know our graph opens up, which means this vertex of 5, 7 has to be a minimum. Okay, next example. We have an A value of negative 3, which we'll talk about in a minute, But as far as my vertex goes, I know it's going to be the opposite of what's in the parentheses. So the opposite of 4 is negative 4. And then it's going to be whatever number is at the end for my y-coordinate. Now I do want to make sure to point out, this is not your y-intercept. Some people think it's the y-intercept. But if we multiply this all out, your c value won't be negative 1. But your k value is negative 1 when we're in vertex form, which is the y-coordinate, not y-intercept, y-coordinate of your vertex. So I know the vertex will be located at negative 4, negative 1. Back to the a value is negative, which means our graph will open down. And if our graph opens down, our vertex, which we know if we were to put it on a graph would be at negative 4, negative 1, will be this point right here, which would be a maximum. Okay, going to our vertex first. We know the x-coordinate is the opposite of what's in the parentheses, so negative 2. And our y-coordinate is the k value at the end, which was 3. So it's pretty easy to find the vertex once you have vertex form. As far as the a value, the a is negative, so our graph will open down. Because our graph opens down, that means our vertex is a maximum. All right, now this last one is a little trickier because I don't have any parentheses, so I don't have an h value. I don't have anything at the end, so there's no k value. So what is my vertex? Well, if we want to rewrite it in vertex form, we could. I could do negative, and then what number is attached to the x, or getting added and subtracted from it? Well, there's nothing there, so that's the same as x minus 0, right? X minus 0 is x squared. And since there's nothing getting added right here, I could say plus 0. So what's my vertex? Well, 0, 0. So this is one of those problems where when we graph it, our vertex is actually at the origin of the graph. We can definitely just determine if it's a max or a min. This is negative. So again, just like these two, if it's a negative, your graph will open down. And if it's opening down, your vertex is at the top. So it is a maximum. This is the key stuff for vertex form. Hopefully you're doing okay so far. All right, write an equation that has the given vertex and opens the given direction. So now we're given the vertex, we're told whether it opens up or down, and we're going to write our own function that matches. So I'm going to do f of x. All right, you could do y equals, that's the same thing. If I want it to open up, what do I know about my a value? Well, I just know that it's positive. So since I didn't specify anything else, I just want any positive number. So I'm going to pick 5. Why did I pick 5? I don't know. I just felt like it. It doesn't matter. It just says make it open up. That will open up. But to have a vertex with an x-coordinate of 2, what needs to go in here? Well, if we want this to be positive 2, this needs to be x minus 2. And then if our y-coordinate is a positive 3, we just put plus 3. So again, we can put any positive number here, but we would need to have x minus 2 squared and plus 3 to get this vertex. Okay, another example. To open down, I know I need to have an a value that's negative. And I think I'll just leave this one as negative, which is the same as negative 1. To have a vertex with an x-coordinate of negative 5, I need to have the opposite in parentheses. So x plus 5. Don't forget the squared, very important. And then to have a y-coordinate of a vertex of negative 1, I just put minus 1. This next one I wanted to open up. I'm just not going to put anything here, because if I don't put anything there, right, that means it's a positive 1, so it's opening up. I want my x-coordinate to be 4, so if I want this to be positive 4, I have to put the opposite. And then I want my y-coordinate to be 0. So I could put plus 0, but if we're adding 0, we don't actually put that. So I'm just going to leave this as x minus 4 squared. That will open up and have a vertex at 4, 0. All right, last example. I want it to open down. let's be crazy on this one. I want to put negative 21. Ooh, yeah, crazy. And then to have this be a 0, I need to do x minus 0 squared. And then to have minus 5, we put minus 5. Now, we never leave x minus 0, so I'm going to actually simplify this or rewrite it as f of x equals negative 21. And this is x squared, and then minus 5. So again, if there's no parentheses there, that just means the x coordinate of your vertex is 0, and then your y coordinate is negative 5. What you might actually recognize, if it's in vertex form and your x is 0, it's actually rewritten in standard form. Crazy. Don't worry about that. All right, this is good stuff. We're almost done. A couple more examples. A type of question that we always like to ask when we're assessing this, so it's something you could see on our evidence of student learning, is taking a function in a different form and then asking you to rewrite it in vertex form or rewrite it in factored form. Doesn't matter which form we're going to or from. But if I asked you to use Desmos to determine the vertex, well, all you would do is you would take this function, you'd plug it in Desmos. Side note, if you don't know how to use Desmos, please work with your teacher as soon as possible to make sure you know how to use Desmos. But if I plug this in Desmos, I get this graph, right? And I know quite a bit of information. I know the y-intercept is negative 27. Hey, that's what this tells me, right, from standard form. But the problem says to rewrite the function in vertex form. Well, in order to rewrite it in vertex form, we need to know two things. First, we need to know the a value. So the a value, I don't need to look at the graph, I look at standard form. What's the a value of this problem? Right? It's positive 1. The second thing I need to know is what is the vertex? Now, we did learn last week how to find the vertex from standard form, right? We can do negative b over 2a to get the x and then plug that in to get the y. But since I have the graph, I'm simply going to look at the vertex, and I know that my vertex is at positive 3, negative 36. Okay, so just by looking at the graph, we know the vertex. If we know the a value and we know the vertex, we should be able to put it in vertex form. We know that our a value goes first, which is 1. If it's 1, I don't actually write it. Then I know I have parentheses squared, and in the parentheses will always be x and the opposite of my x coordinate, so x minus 3. And then the last part, the k of the formula, is the y of the vertex, which is negative 36. So this equation right here, if we rewrite it in factored form, so if we were to actually, in vertex form, thank you, Mr. Dresser. If we were to take this equation and complete the square, we could eventually get it into vertex form. Or we can look at the graph, there's the vertex, boom, negative 3, negative 36, gives me the vertex of positive 3, negative 36. All right, next example, my a value. I just look at my standard form, the a value is negative 2. To get the vertex, I was allowed to plug this in Desmos, so I graphed it, and I got a vertex of negative 1, comma 32. And so to put it in vertex form, I know that a goes first, so negative 2. And then I have x squared, and I need to put the opposite of my x coordinate right here. So the opposite of negative 1 is positive 1. And then my y coordinate gets added at the end. So I have a vertex of negative 1, 32. Boom, there it is. And an a value of negative 2, which makes the graph open down. We can do the same thing if we're given factored form, right? Factored form gives us some different information. It tells us the roots, right? So positive 1 and negative 3, positive 1, negative 3. But if I graph this in Desmos, I can also get the vertex. So the vertex of this graph, right here, negative 1, 12. I know my a value just from looking at the front of the equation. A is negative 3. My vertex which last week we did teach you how to find the axis of symmetry and then plug that in to get the vertex. But because I was able to use the graph, I know my vertex is -1, 12. So to rewrite this in vertex form, what's going to go first? The -3. And then I have my parentheses squared. Since this is a -1, I'm going to put the opposite, +1. And then my y-coordinate always just goes at the end, +12. So this is the vertex form of this graph. One more example. My a value is 1. My vertex, once I graph this using decimals, I got a vertex of -2.5, comma -2.25. Don't be afraid, it's just decimals. We can still rewrite this. Put my a value first, which is 1, so I don't have to actually put it. We want the opposite of -2.5, so that's +2.5 squared. And then my y-coordinate just goes at the very end. And we now have the vertex form of this equation, which tomorrow we're going to start looking at why vertex form is so helpful, especially with transformations. And then when we graph absolute value equations in a couple weeks, it'll be super easy because we understand this vertex form, which is kind of a universal form as far as transformations go. But anyway, back to that problem that we started with. We were given this standard form. We rewrote it and put it in vertex form. And at that point, we didn't really know what this told us, right? That was before we started learning about the vertex form. But now that we have looked at vertex form and hopefully we understand it, what two things do we know? Well, we know that A is 1, so the graph opens up. And because it opens up, it has a minimum. But the other thing that hopefully now we can look at this and automatically notice is that our vertex will be at the opposite of -3, and then our k value, -1. So our vertex should be at +3, -1. And if we look at the graph, 1, 2, 3, down 1, bada boom, bada bing, that has a vertex of 3, -1. It's been my pleasure to teach you today. I hope you guys are doing fantastic. Go Titans.